Now, the last concept of this chapter that we need to cover is something called diffraction, and diffractions is essentially going to be a fancy word for the bending of light. And essentially it's going to be the bending of waves by any mean other than reflection that's going to kind of bend light, and refraction. It turns out that this is going to happen for all waves, not just electromagnetic waves, light waves, but for sound waves as well. And this is kind of what we see around the edges of shadows. Let me just take for a second. Suppose I had a wall like this, and if I were to have something that was relatively loud putting out some sound, then the sound's going to travel kind of like this. And yes, sure, some of the sound is going to get reflected. But if I had a person on this side of the wall, then they're probably going to hear it. Now, if they're right up against the wall, maybe they won't. But these sound waves are going to be able to bend around the wall. And if I had my person, kind of over here, then they're going to be able to hear that sound. It's going to bend around that barrier. So we would say that it's going to diffract. Now, this just kind of shows exactly what I said on the last slide. Suppose, for example, we had some waves in the ocean, and we have these waves kind of coming in like this, and we had a pole sticking out of the ocean. Maybe there's a pier there or something. We know that if we're standing here on the beach, that the waves are going to be able to bend around this pier. And while there might not be any waves just right here on the other side of that pier, maybe it's going to be a bit of an eddy, the waves are going to fill in, for lack of a better word, and what arrives on the beach, as long as this thing is far enough away, is going to be a regular, ordinary, everyday wave. So essentially they're bending in and they're filling out. Light waves also bend. They also do the same thing. And what we can kind of see is, suppose we had some light waves coming in and we had an object right here, then what's going to happen is maybe there's going to be some region right here where it's completely dark, and that would be this region right here, but the light waves are going to fill in, just like this guy filled in, and we're going to start to see fuzzy edges on shadows. Again, it has to be far enough away. If we were to move this object really close to the wall, then we're not going to have a whole lot of time for this guy to be able to fill in. Now, diffraction also is going to support the wave nature of light. And it turns out this fellow by the name of Isaac Newton, we talked about him a whole lot in Physics 101, he believed that light was made up of teeny tiny little particles called corpuscles. And today we actually call these guys photons. But what we could say is, if light was a particle, say this B, this B, this B, this B, and this B, and it were to go through a barrier, or around a barrier, then what's going to happen is it's going to stop this guy, this guy, this guy, and this guy, and only that B is going to make it through and hit the wall. However, that's not actually what happens. What happens is light is able to bend as it goes through this barrier. So what's going to happen is these guys are essentially going to fan out, and we're not going to see just a single spot on the wall, but we're going to see a bright spot right here, and it's going to get more fuzzy as it gets towards the edges. Chunks of light, particles of light, do not support what actually happens here. So for all intents and purposes, light is definitely a wave. However, diffraction is less obvious than the diffraction that occurs in sound. We know when it comes to sound that we can hear the band playing from the band room even when we can't actually see them. So sound definitely bends around barriers. Light bends around barriers as well, but the wavelength's actually much smaller, and so diffraction is less obvious in our everyday life than the diffraction of sound. We could also say that if I were to be standing here and I were to walk through the doorway, then if I were to diffract, then I would start to fan out, and it would probably be a bad day for me. So for all intents and purposes, I am definitely a particle. Now, when it does come to diffraction, size matters, and what I mean by that is if we were to try to pass through a slit, then that slit actually has to be relatively small compared to the wavelength of light for us to be able to see it. Let's just take for example, if I had a light source right here, and it was passing through something big, like a window or a door or something like that, then what we might see if we were to go ahead and put a screen over here is we're going to see a bright spot, and it's going to look just like light behaved like a particle. However, as we go ahead and we make this slit smaller and smaller and smaller and smaller, then we're going to start to see the diffractive nature of light. So here we have a light source, and now we have a very narrow slit, getting close to the wavelength of light. And what we're going to see is we're going to see something more like the way I explained it. And what we're going to see is we're definitely going to see a bright spot right here, but then it's going to get more and more and more fuzzy towards the edges. And that is actually the diffraction of light. Now, the distance matters too. How much space do we give for the light to be able to fill in around the corners? So how close the screen is also makes a difference. Now, if we were to go ahead and look at the screen from the previous slide for the small slit, for the narrow slit, what we're going to see is we're going to see something that looks like this. We're going to see that bright band right in the middle, and I said it's going to look fuzzy off to the side. And the reason why it's going to look fuzzy is actually we're going to start to have alternating bright and dark bands, kind of like the two-slit experiment, but not quite. So we're going to have bright, dark, bright, dark, and actually it's going to die off in intensity as we get further and away from the main slit. It kind of makes sense that it's going to be bright in the middle because that's where a lot of the light is going to be passing through. And this alternating bright-dark is going to make it look fuzzy. Now, if light behaved like a particle, it could never do this. It could never cancel out. Geometric optics can't explain what's going on right here. Light should travel in straight lines, but it doesn't. It's able to bend around these corners. Just a quick little check your neighbor here. When does diffraction occur? I've already said this, but it's going to occur for both sound and for light. Now, how fuzzy the shadow is going to depend on the wavelength of light. It's going to depend on the size of the object, the distance to the screen, so it's going to depend on all of these guys. Now, I kind of want to come back and talk about what's going on here, and I actually need to come back to this idea of Huygens' principle. Remember that Huygens said that if we had some wavefront at some time, then what we can do is we can take this wave crest and we can chop it up into little teeny tiny chunks and say each one of these guys is going to act like a source of its own waves, and it's going to send out circular waves, kind of like when we drop a stone into some water. At some later time t, these guys are going to add up constructively, and we're going to get a new wave crest right here. And these guys, you can slice and dice them up and say we're going to get a new one here, and here, and here. So again, what we're doing is we're chopping this thing into pieces, and we're saying this chunk behaves like a point, this one behaves like a point, point, and point. Now, when we talked about the two-slit, what we did is we said, okay, we're going to take this wave right here, and at this point right here, we're going to treat that like a point source, and we're going to treat that like a point source, and point sources are going to send out circular waves, just like stones do. So circular wave, circular wave, circular wave. And what's going to happen is these two sources are going to add together in some places, and they're going to cancel each other out in other places. Now, this is going to be important for diffraction because what we're going to do is we're going to get rid of this little piece right here, and we're going to say, well, we have a source here, and it's going to look just like this, but a little bit more complicated. Again, what's going to happen is this thing called diffraction, and that's going to be the fanning out of light. And you can kind of see that with a two-slit, it does fan out, and with the single slit, with diffraction, it's going to fan out as well. That's more or less what diffraction is. It's the bending of light when it goes through small openings. Now, with the two-slit pattern that we talked about, kind of what I said was, again, we're going to treat this like a point, we're going to treat this like a point, and directly in between them, we're going to have some bright area. Then we're going to have some dark area where they're out of phase, and then bright and dark, and so on and so forth. So we have this alternating pattern. With the single slit, all we're going to do is we're going to get rid of the middle little chunk right here. So essentially, all I've done is I've gotten rid of this stuff right here. And we could actually make the same argument, where if this is a point and this is a point, then there's going to be a really bright spot in the middle. For every piece here and here, they're going to add together in the middle. For every piece here and here, they're going to add together in the middle, here and here, and here. So it makes sense there's a bright spot in the middle. And pretty much between here and here, there's going to be a really, really, really big bright spot. But if we were to start talking about somewhere up here, then it would make sense that this piece and this piece might arrive out of phase. So there's probably going to be a dark spot here and a dark spot out here, and then bright, dark, bright, dark. And more or less, that's why we see this single slit interference pattern. Now, the bright spot for the single slit pattern is going to be bigger because we have all of this real estate to kind of cover. We're going to see this really big bright spot, and then we're going to see a dark spot, bright spot, dark spot, and technically the intensity is going to die off as we move away from the bright spot. The reason for that has to do with the fact that we have a big opening rather than two small ones. And when I say big, I'm still talking relatively small. It's going to be around the wavelength of light. Could be bigger, but not very, very, very big. What this kind of boils down to is some of the waves are going to arrive out of phase, and we're definitely going to get dark spots. Again, light is definitely a wave at this point. We can see diffraction, can see the bending of light. If we were just to talk about water waves and think back to when I had this board and I was pushing it back and forth, sending out plane waves, so plane wave, plane wave, plane wave, Huygens' principle says we can chop this up into little teeny tiny pieces, and each one is going to behave like a point source. And this one looks like I could chop it up into two pieces. It's going to send out waves like this and like this. They're going to constructively add together, and you can see it's really sharp right here, and you can see it looks really fuzzy right here. So we're probably going to have constructive interference here and destructive interference along this path and along that path. Now, think back to what I said earlier about the size of this opening. If we were to talk about this opening being relatively large, say kind of like this, then we're going to have lots of point sources in the middle, and the image is going to appear to be slightly fuzzier. If we wanted to go ahead and make this thing really, really, really small, then maybe we're only going to have one point source right in the middle, and the waves that come out on the other side are going to be crystal clear. Now, it does turn out that the wavelength matters when it comes to diffraction, and it's also going to depend on the size of whatever is obstructing it. Let's just consider for a second that suppose I had some jetty sticking out in the ocean, and if I were to have some waves kind of coming in, then what I can do is I can chop this thing up and say Huygens' principle applies, and this guy's going to act like a point source, this one will act like a point source, and so on and so forth. These guys are going to propagate just a plane wave, and this one's going to fill in over here. And this is going to act like a point source. It's going to send out spherical waves, going to end up here, and so on and so forth. So what we kind of see is we kind of see this wave being able to fill in right here. Right over here, there's not going to be very many waves. If this was light waves, we would say that it's dark here. But we can kind of fill in behind objects. We can get that fuzzy shadow, if you will. So right here might be dark, right here might be gray, and right here might be bright. Now, let me just consider the case where here I'm going to have the wavelength roughly equal to the size of the object. And you can kind of see the wavelength is going to be the peak-to-peak distance, and here I have my object. So these guys are roughly equal. Now, what's going to happen here is this guy's going to act like a point source, this guy's going to act like a point source, and it's going to start to fill in, and then these guys are going to act like a point source, this guy is going to start to fill in, and we can fill in behind this object relatively easily because these guys are relatively far apart. And as long as the screen is far enough away, of course. Sure, it's going to be dark in this region right here, but we can fill it in. This is the case where the wavelength is relative to the size of the object. Now, if for a second we were to talk about something where the wavelength is much smaller than the object, so here we have this case where the wavelength is only that distance right there, this is going to be relatively big. And what's going to happen here is sure, these guys are going to act like point sources, but the next one's coming relatively quickly. And so here you're going to see this really, really, really big shadow region. This is going to be essentially dark, and it's not going to be able to fill in. This guy right here is going to be dark, and then right here we can say it would be gray, and right here would be bright. Here it's going to be dark, and here it's going to be kind of bright. Now, let me just make an analogy of this. Let's consider a cruise ship in the ocean. The cruise ship, it would be this guy right here, and it's going to be much bigger than the waves of the ocean. And if you look behind a cruise ship, you're going to see a big eddy region. In the language of light, this would be dark. The reason for this is because the waves are much smaller than the object that we're trying to go around. If, however, we were to have a buoy or a person or something like that in the water, then that object is going to be smaller than the waves or on the same size of the waves, and the waves can fill in around a buoy or a person or something like that. So that's kind of my analogy for water waves, and the same thing applies to light. Now, what this boils down to is actually this is going to limit how well we can see various objects in, say, a microscope or a telescope or something like that. If the object is the same size as the wavelength, then it's going to appear to be blurry. Or maybe you're not even going to be able to resolve it at all. Consider this case right here, where this is my wavelength and this is my object. The object is much smaller than the wavelength of light, so it's going to fill in relatively quickly. And maybe we can't even see this teeny tiny object. What we need to do is we need to perhaps probe this object with the case where the wavelength is on the order, or hopefully smaller than the object. So here the wavelength is going to be roughly the same as the size of the object, and we're definitely going to cast a shadow here. This is kind of why we can't see atoms with an ordinary everyday microscope. We have to probe them with an electron microscope if we want to get really fine detail. Now, other applications of diffraction is how come if you were to drive out west, you can get AM radio, but you can't get FM radio? Of course, nowadays everyone has satellite, but it is what it is. My dad and I took a trip out west, and there were places where we could only get AM radio. There was no FM stations whatsoever. The reason for that is because you get better radio reception with the longer waves. They can bend around objects far more in AM than they can FM because the wavelength is longer. Dolphins actually use long wavelengths to probe far away, and then they use shorter wavelengths to give them finer detail. Now, just really quickly, we do see diffraction not just for single slits, but for circular openings as well, so think about pinhole cameras and stuff like that. And it's just going to look like circular diffraction. So pretty much everything that I said, only now we're talking about circles, and we are going to see a nice bright band, and then a dark, and then a bright, and then dark, and bright, kind of dying off in intensity as we get further away from the center spot. Now, applications of this is, suppose we're trying to look at two stars. Well, the size of our hole relative to the wavelength of light is going to matter. And we could talk about a resolution limit. How well can we resolve something? And really, it's related to how big the opening that we have. If it's small, then we can see things with much finer detail than if it's big. However, the problem is when it's small, not a lot of light makes it through, and that makes it something where we have to get a time exposure. Consider the case of two stars, and we're trying to project them onto a wall. Then if our hole is relatively big, then we're actually not going to be able to resolve these guys because of this poor thing called diffraction. They tend to blur together. You make the hole a little bit smaller, and we are able to see separate images because there's less diffraction going on. Now, when are we best able to resolve stars? It's going to be when there's a small hole, not a large hole.